All right. So in the previous lecture, we talked about Tutber's formula, which allows us to say the size of maximum matching. So let me rewrite the formula here. So number of vertices of the graph minus twice nu of G is equal to maximum of the number of other component in G delete X minus X. Now, what's going to happen if you have a set X which have equality? What's the structure? What can you say? There are things we can say. So you have an X, and there are odd components, even components. And I knew already that each odd component will have at least one vertex that is going to be paired with X, or it's not covered, right? Some vertex. But since we have equality, you cannot have two vertices that are not covered by a matching, maximum matching in M. So if X gives an equality and M is a maximum matching of G, then the only possible situation for an odd component is to have a precisely one vertex that is not covered by M, or precisely one vertex that is joined to a vertex in X by a matching. So each odd component has precisely one vertex that is either not covered by M or is joined to a vertex in X by an edge in M. And what's important is precisely one vertex, because if you do have more than one vertex, then you will not, this is the number of vertices not covered by maximum matching. You will have more vertices not covered by maximum matching. That means it's not a maximum matching. All right. So I knew already that whenever I have equality, then maximum matching cannot cover, but in each odd component there is one vertex that is not covered by a maximum matching or joined to a vertex in X. And moreover, I knew already that every vertex in X is joined to somebody in odd component, and because of that, X have already pairs in other components, so the even component has no option but to have a perfect matching. So all even components will have a perfect matching, right? Because otherwise you will have more vertices not covered by matching, which means that it's not maximum. Right? So all even components have perfect matchings. All odd, and we knew already what happens with odd components. All vertices in X are matched by M to distinct component, distinct vertices in distinct components. Okay, I didn't have to say this. These vertices in distinct components by M. Now, one may think that this is a reasonable description of the structure of maximum matching, but but we want to have a kind of a converse. So what kind of converse do we want? We want that maybe we can build all maximum matching by picking a vertex that my maximum matching will not contain, will not cover, and then build a maximum matching avoiding this particular vertex. So the question to ask is, do we have a converse? Do we have a kind of a converse? Right? Can I pick a vertex V to be avoided by a maximum matching, and can you pick a vertex V to be avoided by some maximum matching? Okay, let me say, can you pick a vertex V to be avoided? Okay, let me a more precise statement would be, for any vertex that we pick, can you find a maximum matching not covering that vertex? Right. I mean, vertices and other components, it seems that for some vertices I have a maximum matching, like this vertex, I have a maximum matching avoiding this vertex. But can I pick some other vertex and say, is there a maximum matching avoiding this one? And this was answered by the Galai and Edmonds. So what we're going to do is Galai Edmonds structure theorem. So let me define the partitions first. So D of G is the set of vertices that a graph has a maximum matching avoiding V. So you have a maximum matching making V a single, right? And A of G is the neighborhood of D. Let me, even though we defined set of neighbors to be n of some set to be set of vertices that are neighbors of vertex in that set and that are not in D, but okay, I mean, probably we don't have to write this, but I'm writing just for clarity. And C of G is the set of vertices minus D of G and A of G. So then DG and AG and CG is a partition, just by definition. So D of G are the people that can be avoided by some maximum matching, and A of G is the set of neighbors of D of G, and C of G are the remaining. So there's no edge from D to C. Now, what can we say? So if you have a, so I mean, this DAC is canonical, right? I mean, whenever you have a graph, this definition is already defines DAC without any confusions, right? There's no different partitions. This is a canonical partition of graph. Now, what this structure theorem of Galai and Edmonds describes how you can build a maximum matching avoiding a vertex in D of C, right? If we know this partition D, A, C, how do we build a maximum matching, avoiding that? Avoiding particular vertex that I pick, right? If I pick a vertex here, how can I find the maximum matching avoiding this? And how does it look like? And the statement of the theorem doesn't explicitly say how to build it, but once you understand it, you will see how to build it. We are assuming that we have some way to find the perfect matching. But anyway, here's the structure. So the first property is for every component C of GDG and of every vertex V of C, C delete V has a perfect matching. And then second, so that means C delete V has, so you have a component here, and in each component, if I delete any vertex, the remaining has a perfect matching. So these become the odd components in G delete AC. Is clear? Right, because when I delete AG, there's no edges from D to C because A is the set of neighbors of D. And this statement says that I can delete one vertex and has a perfect matching. If you have a perfect matching, you have even number of vertices, but you have one more vertex. So if this is true, then they become odd components. What about second property? G bracket. So the induced subgraph on C of G has a perfect matching. So what does that mean? That means you have, so C of G may have many components. Each component will be even components because each component has a perfect matching. So these are the even components. And second property implies that these even components have a perfect matching. So if I know how to find the perfect matching, then I can just combine, find the perfect matching in C of G and find the perfect matching in, which can be used later to build a maximum matching of the whole graph, avoiding this particular vertex. Okay, what is the third property? And this is an interesting property. Okay, for any subset S, which is non-empty, if I take a subset here which is non-empty, then there are at least S plus 1 components G, D, G having neighbors in S. So if you remember the last part of Touch theorem, we proved something like this, except we were using a Hall's theorem, so there was no plus 1 condition. Right? Should I remind you? Yeah. So we were in the last parts of Touch theorem. Oops. We were proving this by using Hall's theorem, and it just said a number of yeah, I mean, this gets contradiction, so that means number of other components having neighbors in S is at least S. And that was how we proved that there exists the perfect matching. Now, what we are saying here is we have extra one. We have one redundancy. Why is it useful? Later, let's say I pick this vertex to be avoided. So that means when I find the matching between A of G to the other components, I don't want to use this component because I declare that this is the vertex that I want to avoid by a maximum matching. So I delete this component from the graph. Then in the remaining, I want to find the matching between A and these remaining other component, and the matching has to cover A. And how do we guarantee? Since I have an extra one, even if I delete one other component, I still have at least as many components having neighbors in S. And this is true for all S, all subsets of A, right? And I can ignore anything on empty set. And then by Hall's theorem, we can find the matching covering A and not using these components. So that's how I build a maximum matching. And let me say the last property. I mean, 1, 2, 3 already is enough to say the following. The number of vertices of G minus twice nu of G is equal to the number of other components in G delete A of G minus size of A of G. Okay, why is this the case? Right, by the second property, I have a matching covering everybody here. By the third property, I can cover A by a matching between A and other components. Not using this particular one because I have extra one, so I can delete this and join these to distinct other components. Now, by the property 1, for each other component, if I have joined an edge, I can find the matching covering all the remaining vertices. If I don't have any edge joined with A, then I pick any vertex and remaining I can cover. So the number of vertices that are not covered by my maximum matching is precisely the number of components minus size of A. Right? So the number of components minus size of A is precisely the number of vertices not covered by matching induced from built from these 3 steps. So that gives you equality. And once you have equality, then that means this is new. Okay? So 1, 2, 3 are the key property, and that describes how you build the maximum matching. So let me say that way. So any maximum, okay, for any vertex free in D of G, we can build a maximum matching avoiding V by first taking a perfect matching of G induced on C and finding a matching in a bipartite graph between A of G and odd components not containing A to cover A of G with the to match A of G with the vertices in distinct component. Okay, so I shouldn't say odd component. I can just say components of G dg not containing A. So distinct components of G dg. And then finally taking a perfect matching of C delete V, no, not V, okay, let's say W for every component of G dg where W is equal to V if C contains V and W is a vertex match it to X by the second step if such a vertex exists, or W is any vertex otherwise. Any vertex in the component. If you don't have any vertex, I mean, if this component doesn't contain V and if it's not matched to X, no, not X, it's A of G, right? So what I'm saying is, if we knew that this is true, then I can build them for any vertex. I can build the maximum matching, avoiding this particular vertex in D by these 3 steps, and that describes how you build the maximum matching, avoiding particular vertex. Okay, so it's enough to prove this statement, this 1 to 3 statement that will imply this and all these descriptions. Okay, so let's see how we prove it. So first step, okay, so what we are gonna do is somewhat indirect. We will have a lemma saying the following. Okay. So how do we prove a lemma? So the lemma is as follows. There exists a subset U of V of G set is such that every even component of G delete U has a perfect matching. Every odd component C, okay, so for every odd component C and every vertex V of C, C delete V has a perfect matching. So it's component of G delete U, and we want to have more properties. So let's say this is 1, this is 2, and 3 for all s subset of u which is not empty. There are at least s plus 1 odd components of G delete U having neighbors in S. So this is what I'm gonna prove instead. Why? It's the same statement actually. It's the same statement. This lemma just says that there exists a subset U so that 1 and 2 and 3 holds. Like if you have a property, if you have these 3 property, what does that mean? By the same logic, I can build a maximum matching, avoiding any vertex in the odd component of G delete U. Which means that A of G, no. This means D of G must contain vertices in an odd component of G delete U. And moreover, this already implies that this thing is true. The number of vertices minus twice nu is equal to number of odd components G delete U minus U. So that means yes, no vertex outside odd components will be in U, will be in D of G, because they cannot be avoided by maximum matching. So, which means that D of G is equal to vertices in an odd component. All right. Now, what about A of G? Any vertex in U will have a neighbor in. By second property, any vertex in U, third property, any vertex in U, if I pick S have size 1, they will have neighbors in odd components. So that means A of G will contain U. But actually it's equal, right? Because you cannot have any neighbors. You cannot have any neighbor in even component. So C of G is going to be equal to the odd component, the even components. But this is in even components of G delete U. So instead of defining DAC first, I can just say, well, there exists the one set U satisfying these 3 property. And because of that, this lemma doesn't explicitly say that there exists a set. It doesn't explicitly say that U is equal to A of G, but essentially this set is unique, right? Because it has to be equal to A of G. Okay, so that's what we're going to do. So proof of the lemma. And that's enough. Right. So let me write U is unique. And this proof is due to Kotlov in 2000. So if you want to look for the paper describing the proof, you can look at his paper. So what we do is define this function, that f of g, u be the number of vertices in odd components of G delete U. Okay, and we choose U such that it satisfies top-Ferret's formula. So number of vertices minus twice nu of G is equal to the number of odd component in G delete U minus size of U, and this function is minimized, right? There's at least one choice, one set, which achieves the equality by top-Ferret's formula, and among all sets, there are only finitely many sets, so therefore there is a set which gives a minimum possible value. And we already know that there is a maximum matching of size satisfying this equality. So this implies that if you do have a maximum matching, then every even component will have a perfect matching. So 1 is true already. Now let's try to prove 2. So what is 2? Imagine that there's a, so let C be another component of G delete U and V be a vertex. If C delete V has no perfect matching, what can happen? Right, so here's a U, here's a C, there's a vertex V. If it doesn't have perfect matching, I can delete something, and then the remaining I have too many other components, right? So by touch theorem, C delete V delete X has too many other components. Right. Now, what does that mean? Right. And C minus V has even number of vertices, right? Because it was odd components. So remember, because of the parity, this plus X has equals parity with the number of vertices in C minus V modulo 2, right? So that means number of odd component in C delete V minus X is at least X plus 2, right? Because this means C delete V delete X has the same parity with X. So they are both even or both odd. Okay? And that's key. That's the key property. Now, let's think of U prime be the U union V union X. Now it's now this will be my new set U prime, and see what happens. The number of other component in G delete U prime minus U prime is equal to, okay, so number of other component in G delete U prime. So what are them? Right, these are the one instance. So that's those odd components stay as odd components. So that's this number plus there used to be initial odd components minus 1, and U prime has size U minus 1 minus X. And what does that mean? This is, and I know that this is at least X plus 2, and number of other component G delete U minus 1 minus U minus 1 minus X. So that is number of other component G delete minus G delete U, and these two this cancel each other, and these two cancel each other, so that's equal to this, right? Remember that U is chosen to maximize the number of component in G delete, right? Because that's what top variance formula is. So that means number of component of G delete U prime minus U prime is still equal to number of component of G delete U minus U. So remember our choice of, do you remember our choice of U prime? It's chosen to satisfy this equality, and this satisfies that equality. So it's okay. How about f of G U prime? That's the number of vertices in other component. We have deleted at least one, so this is strictly less than U. So it's contradiction because we chose it to minimize. We chose U to minimize f of G. So that means, so that second property holds, right? C delete V has a perfect matching. Now let's look at the last property. Why do we have a Holst condition with extra one property? So suppose that. So we have U and we have S, and number of other components having neighbors in S is too small, is at most S. Now what can you do? Let U prime be U minus S. So this is U prime. What is the number of other component in G delete U prime? Minus U prime. Well, the vertices, so these are having neighbors here. So those other components have no neighbors to S, and they stay as odd components, right? So it's at least the number of odd component of G delete U minus, so the number of odd components here is at most S, so we are deleting S. It could delete more, so I have an inequality. No, it could delete less, right? So the number of other components at least this minus U prime, and then what is this? So this is same as number of other component of G delete U minus U. So again, by the same logic, the number of other component of G delete U prime minus U prime is equal to number of other component of G delete minus U. But f of G U prime, the number of vertices in the odd component is strictly less than f of G U. So that's contradiction. Okay, so that proves the 3. All right, so that's the proof of the Gallai-Edmonds structure theorem. So now you can say that whenever I have a graph, I can decompose it into 3 sets, right? And any maximum matching look like something, and conversely, if I pick any vertex in the other components, you can build a maximum matching, avoiding this vertex. Okay, so that's the proof of Gallai-Edmonds structure theorem. So that's it.